For several videos, we have been talking about linear ordinary differential equations. And in this video, we'll talk about partial differential equations. So these are equations in which the function for which we're solving may depend on many variables, and we may take derivatives with respect to all of them. And so it's beyond the scope of this course to develop a systematic theory. So we'll mostly focus on a few examples of physical importance, which have connections to physics. One of our main examples will be the heat equation. Let us try to understand how heat flows in a medium. So, and for simplicity, consider a one-dimensional case. It means that either you should imagine the substance is one-dimensional or close to it. So it's a very thin wire or very thin beam, or just the temperature is constant in two other directions. So it only varies in one of them. And we'll moreover imagine that the material in question is uniform. So its properties are the same along the everywhere in the material. Now imagine we add some energy or heat to the system, and temperature will change proportionally. So per unit time, change in temperature is the ratio of change in heat over the amount of the material. So we need to quantify it a little bit, but basically the more change, basically the more change we put in, more the energy difference we put in, the more change in temperature it triggers. And then say the less amount of stuff we have, so the smaller is the density or the mass of the material, the faster temperature changes. As it also turns out, having a temperature difference causes heat to flow proportionally to the difference. So per unit time, heat flow is proportional to change in temperature over distance to which it flows. So let's try to write this in terms of letters, variables. So u of x and t will be the function which will give the temperature at position x and time t, and capital H of x and t for the heat flowing. So u is measured in kelvins, and H is measured in joules or in any other energy unit. So then this relationship, the first equation is this, right? So the change in temperature per unit time is proportional to change in heat per the amount of stuff, also per unit time. So the variation, this little change of delta u of xt over delta t, is proportional to delta h of delta x and delta t. And the second equation, that the heat flow per unit time is proportional to change of the temperature per distance flows, says that delta h over delta t is proportional to delta u over delta x. So if you combine the first equation with the second equation, and we'll replace in this small differences with derivatives, so assuming that those derivatives exist, we'll get the famous heat equation, at least up to proportionality coefficient, that the partial derivative of u of the temperature with respect to time is proportional to the second partial derivative of the temperature with respect to the distance. Right, you simply plug in delta h over delta t into the second, into the right-hand side of the second equation, and that gives you the second derivative on the right-hand side. So first derivative of time is proportional to the second derivative with respect to the coordinate. This is the heat equation. So we need to put some proportionality constants. Let's call it beta. So this constant will depend on properties of the substance, heat capacity, the density, thermal conductivity, but overall it's a positive constant. Now, let's talk about how we will approach the solution of this equation. So the analog of the initial value problem in the setting is the following. So we should specify the temperature distribution. So U is a function of X, say in the wire, at some initial time t0. So this is the data of a function in one variable, right? Because the second variable has been evaluated at t equal to 0. And one should also say how the ends of the wire will behave during the whole evolution. So let's talk about separation of variables method to solve this PDE. So recall that the linear vector ordinary differential equation can be written as this. So if vector u is a function with n components and its time derivative is equal to a and by a matrix multiplied by this vector. Given a function of two variables, one can specify one of the variables to get a function in the other. So u of x0 and u of x1 are simply functions of x. So one way to think of a function of two variables like u of tx is that it's a function of t valued in the vector space of functions in x. So in a sense, this t dependence is sort of kind of foliated, it's fibered over the x dependence. So the heat equation, d over dt u is equal to beta d2 over dx squared u of xt. We can write it like this, where now the vector space v, in which the function u of t takes values, is replaced by the vector space of functions in x. And the linear transformation A on capital V on this vector space is replaced by the linear transformation, the second derivative operator on the space of functions of x. So we know how to solve this equation. So given an eigenvector V of A with eigenvalue lambda, a solution is given by the exponent, right? So it's a V multiplied by e to the lambda t. So in order to solve the d over dt u of xt is equal to beta d2 over dx squared u of xt, we want an eigenvector v of x of this operator in the right-hand side, beta d2 over dx squared. And let's call it an eigenfunction. So it's eigenvector is actually an eigenfunction with eigenvalue lambda, and then the solution will be given by v of x e to the lambda t. Right, so it's a complete analogy with the ODE, with the vector ODE case. So finding an eigenfunction of this operator with eigenvalue lambda means to solve this equation. And so the second derivative acting on v of x equals to lambda v of x. And we know how to solve this ODE, right? Its fundamental solution is given by increasing and decreasing exponentials like this. Well, depending on the eigenvalue of lambda, so it's e to the x root lambda of a beta and e negative x root lambda of a beta, where we'll have to replace this by sine and cosine if they are, if it's an imaginary, if those square roots are imaginary. So for some solutions to d over dt u of xt equals beta d2x d2 over dx squared u of t, the heat equation are given as follows. So it's the exponential in time e to the lambda t multiplied by another exponential solution in x if lambda is bigger than 0. Now, if lambda is equal to 0, then we just have a linear dependence in x multiplied by the exponential dependence in time. And for negative lambda, we have oscillating behavior. So we have e to the lambda t multiplied by the combinations of sines and cosines. So for the equation d over dt u of t equals a u of t, we can get more solutions by taking linear combinations of those. So if you take all the above solutions and then add them together, it would still solve the the vector equation. Suppose our system is a wire of length L, in which this temperature at the ends is fixed to 0. So it's a boundary condition at those endpoints. And let's coordinate our wire. Let's coordinate our wire to run from 0 to L along the x-axis. So this constrains which functions in the previous expression are allowed. So in the presence of these boundary conditions, we can think of it as a restriction, saying that we are considering solving the equations inside the vector space of functions with these boundary conditions, so that the temperature vanishes at 0 and at L. So we can impose those boundary values as follows. Those expressions, the x dependence is presented as the linear combinations of exponentials or trigonometric functions. Now, which of them can possibly vanish at the same time at 0 and L? So the first solution, the exponential one, evaluates to these two conditions, right? So if x is equal to 0, we have a lambda plus b lambda is equal to 0, and f is equal to x is equal to L, have the second constraint. So, and then basically the only solution is that when those coefficients are equal to 0, right? Because this inequality never happens. Now, if you take linear dependence, we can also conclude that all the coefficients are equal to 0. Right, so the only linear function, basically, which is has 0 slope, is just the 0 function, which passes through the origin. So finally, we have to consider trigonometric solution. So the vanishing at x equals to 0 implies that a lambda is equal to 0, right? Because well, sine is equal to 0. And then the vanishing at x equals to L implies that L multiplied by root of negative lambda over beta must be an integer multiple of pi. Let's call it a capital N times pi. So here's the condition that therefore lambda is equal to negative beta multiplied by square of this ratio and pi divided by L. So in total, the solutions which obey the boundary value conditions look as follows. So we can take, so any of those solutions for every given n will satisfy the equation. So we can add them up together. So this is, remember, lambda is that coefficient from the previous slide. So we put it in here. So it's e to the negative lambda t times sine n pi over L x. And then we sum it from n over n goes from 1 to infinity with some coefficients Cn. So this is the a generic solution that obeys the given boundary value conditions. So we can also now we can blend in the initial conditions. So in that, and we can consider initial boundary value problem. So consider a wire of length pi. For convenience, right? So that the like eigenvalue would look a bit more natural. So we have a stretch of the wire from x equals to 0 to x equals to pi. The coefficient beta is equal to 1, and say that at time equals 0, the temperature distribution looks like this. So it's the sine of it's a linear combination of the 3 sine functions. So sine x, 3 sine 2x, 5 sine 3x. So we can ask ourselves, what's going to happen if you wait for 1 second? Like, so how will the distribution look like when we let the heat flow through the wire for 1 second? So we take the previous solution, like, so that was the generic solution with given boundary conditions, substitute beta equals 1 and L equals to pi. So we get this equation. So u of xt is equal to the sum coefficient Cn e to the negative n squared t sine nx. And we can ask for this to agree with the initial condition over here. So this function at t is equal to 0 should give us this expression over here. And we immediately see that that implies that coefficients C1 is equal to 1, C2 is equal to 3, and C3 should be equal to 5, and all other coefficients must vanish because there are no higher sine functions in the initial condition. So at this moment, you can probably ask me, why did I choose such a specific right-hand side? Well, it's for now, it's for simplicity, but then when we'll be talking about Fourier transform, Fourier series, you'll see that essentially any function can be written as a possibly infinite sign of sines or cosines, depending on the symmetry of the problem. Yeah, so you plug those in, and this will be your answer. So u of x1 at t equals 1 will have the following special distribution of temperature, yeah, with these coefficients. Now let's talk about the wave equation. Consider a string stretched horizontally between 2 points, but it's free to vibrate up and down. So we'll write the equation y of xt for the height at the horizontal position x and time. So we'll have, so say if string is not vibrating, so it's fixed here and fixed there, and when it vibrates, it can produce those waves, those sine functions, sine-shaped curves, right? And then this will be the x direction, and then we'll see how this, and then in the next moment of time, it would look like this, and so on. So we'll record y of x of t for the height, right? At the position of the piece of the string at coordinate x at the moment of time t. So it turns out that the vibration is governed by this wave equation. So we can discuss the derivation in a different video. So it's the second derivative in time of y is equal to another coefficient, which you call alpha squared, times the second partial derivative of y in x. So in this case, second derivatives are proportional to each other, as opposed to the heat equation. So you can derive it by imagining that the string is made up of infinitely many tiny springs, and then using the Hooke's law and the F equals ma, Newton's second law, in order to derive it. But let's leave it from now. Let's focus on how to solve it. Again, we can rewrite this as the second order vector ODE. So the second derivative of time acting on the vector function y is equal to some matrix A acting on the vector function y. So given an eigenvector v of A with the eigenvalue lambda, we would get solutions of this exponential form, A exponential to the root lambda t plus B exponential to the negative root lambda t for positive lambda, or trigonometric solutions for negative lambda. So for the vibrating string with endpoints fixed at 0 and L, the operator A in this equation is replaced with the operator alpha squared d2 over dx squared on the vector space of functions in X, which vanish at 0 and L, right? Because at those points, strings is firmly attached to the anchor points, and it does not move up or down. So we saw that the eigenfunctions for alpha squared d2 over dx squared with these boundary conditions are given by sine n pi x over L with eigenvalue negative alpha squared n pi over L squared. So it's the same eigenvalue problem for this operator, right? So we don't have to redo it again, as we already did for the heat equation. So the corresponding solution to the wave equation must look like like this, right? So the time dependence goes like this. It's a oscillating behavior as expected, multiplied by oscillating behavior in the in X. And more general solutions will be given as linear combination of those, which we can also put in the series.